Okay, here we are. Welcome to lesson 3 for magnetism, the final lesson in our magnetic field topic. So this is it. Normally we would take a quiz after this, which we cannot do because obviously we're not in school. So tomorrow, which should be Tuesday, we will move on to the waves topic. So today's topic is Magnetism 3, magnetic field around a long infinite wire. As I mentioned, electricity, moving charge is what creates magnetic field. So these diagrams illustrate the pattern of magnetic field. So imagine a wire, let's see, where did I put my wire? Okay, so imagine a wire coming out of the paper like this, okay? The electricity, and it comes from behind the paper. So we got a wire going like this, and it's very long, and maybe it stretches 100 feet either direction. And the current comes out of the paper, so that's why we have that, again, circle with a dot in the middle. That represents like an arrow pointed directly at your eye. The shaft of the arrow and the tip of the arrow. In this situation, the magnetic field, this is the pattern. You would see it going around in a counterclockwise direction like this, okay? And the weaker you go out, that counterclockwise direction still is there, but the arrows get smaller. The magnetic field gets weaker the further you get from the wire. But at a given radius, it's all the same magnetic field. If we had in that wire a current that goes into the paper instead of out over here. So again, we draw a shaft, the shaft of the arrow, and the X representing the feathers of the arrow on the back of the arrow. The magnetic field has the same pattern as here, but the arrows switch around and go clockwise instead. That is how electricity creates magnetic field, going around the wire. Not like a positive proton electric field points away everywhere. It goes around a wire, magnetic field. So, how do we find the direction, clockwise, counterclockwise? We use what's called the right-hand rule. Step 1 is you point your right thumb. How many students use their left thumb? A lot do. You'd be surprised. You got so much going on in the quiz, the test, whatever, you forget and you start using your left hand. Make sure it's your right hand. Your right thumb points in the direction of the current. So in this case, I point my finger out of the paper like this. So then the four fingers naturally bend in the direction of the magnetic field rotation. So you see my fingers go around this way, counterclockwise. Your fingers don't tell you the direction of the magnetic field. For example, if I said, what's the magnetic field down here? You go, oh, to the left. Not correct, because it's to the left up here, but it goes around, round, and to the right over here. So your fingers don't tell you the direction of the magnetic field, they tell you the direction of the rotation. If I use the right hand rule over here, thumb goes into the board for the direction of the current, and you see my fingers go this way. So they go in the clockwise direction, and the magnetic field goes like that. The magnitude is given by this equation. Mu 0 is a constant. This is like the friction coefficient. The subscript is a 0. I, 2 pi r on the bottom. Mu 0 is given by 4 pi times 10 to the minus 7 Tesla meter over amps. Magnetic field measured in Teslas, by the way. I is the current in amps, and R is how far you are from the wire in meters. Here's another example using the right-hand rule. We have a wire running along the paper and electricity flowing to the right. So what is the pattern of the magnetic field along the paper? I use my right-hand rule. Thumb goes this way, and I see above the wire, my four fingers come out of the paper. Magnetic field. Again, this doesn't tell us the direction of the magnetic field everywhere, just the direction of the rotation. So out of paper and then rotates, and over here it's going to go into the paper, like this, into the paper. And also, big magnetic field, weaker, because as radius gets bigger, less magnetic field. Okay? All right, here's one final example, complicated example. I got two wires, and I want to determine the magnetic field net in between the wires. They're 0.2 meters apart, 0.1 meter, 0.1 meter to that point. So that's what the radius is. How far away are we from the wire to this point? 0.1 meters in both cases. I got 2.5 amps into the paper here, 8 amps into the paper there. Using my right hand rule, that's the first step I'm going to do. I put my thumb in the direction of the current here, and I see my forefingers point this way. So the magnetic field caused by wire 1 points towards the bottom of the paper like this. I use the right hand rule over here for this wire. My thumb goes into the paper and I see the magnetic field comes around and comes up. So this wire creates a magnetic field towards the top of the paper. Because of the larger current, I know it's going to be a larger magnetic field. So I use the formula from over here, B equals mu 0 I over 2 pi r. And I plug in mu 0, the 4 pi times 10 to the minus 7th. Not on the reference table, by the way, because again, this is a little bit beyond the Regents curriculum. I'm putting it in here just to round out magnetism so we get most of the main topics in our studies. So, and then we put the current 2.5 amps and then 2 pi over the radius of 0.1 meters. And I get this for the magnetic field pointed in the downward direction caused by wire 1. Okay. Wire 2, I repeat the calculation but put 8 amps in here. Same radius, same mu 0, same 2 pi there, and I get this number up. That's that arrow. And then because I want to find the net, when I have arrows, just like with forces, when they're in opposite directions, you find the net through subtraction. If they were both in the same direction, we would add the two, obviously, and we get the net magnetic field. So there is lesson 3. We are now done with magnetism after you do this homework. Again, look at the homework, do it, and indicate on the Google Sheet any questions that you have so I can answer them so you're not leaving questions unanswered. So that's it for magnetism, and I'll say goodbye or hello to everyone, and look forward to the next video on waves.